So we previously talked about Bernoulli's equation and some of its relations, but I want to get into some of the depth behind it and some of what it truly means and how to use it. Because I think this is a very, it's profound, but it's actually going to be a restatement of conservation of energy, because the idea of conservation of energy is just so incredibly profound that it is, and so incredibly useful that you find it just everywhere. Okay, so get my paper positioned correctly. There we go. So let me rewrite the equation again. So Bernoulli's equation. So the equation says pressure plus 1/2 rho velocity squared plus rho gh equals a constant. So what I want to do is I want to rewrite this equation just slightly. So this is going to be force per area. This is going to be mass per volume. So I'm going to try and write my, I'm going to do V like that. I can have a curly V. It's going to be velocity. I'm going to do capital V as volume, just for your notations, because there's too many V's. V squared plus m over velocity gh. That's constant. So now I want to multiply both sides of this equation by the volume. So I want force over area times volume plus 1/2 m v squared plus m gh equals a constant. And this is a different constant, but we can do constant times v if you want. You want to keep track of it. It doesn't really matter, just different constant. So now I've gotten two terms that look a lot like energy, right? Because that looks like kinetic energy. That looks like potential energy. So, but what's this term on the left here? What is that? Well, what if I rewrite volume and say volume is equal to area times height or depth or something like that, some other variable. And then I can say, well, I can cancel that area with that one, right? So now I'm going to get a term that looks like force times distance of some sort plus 1/2 mv squared plus mgh equals a constant. Right? I'll call it constant prime. So now this first term looks a lot like work, doesn't it? So we actually we're going to have a term that looks like work, a term that kinetic energy plus potential energy is a constant. So Bernoulli's equation is really just a statement of conservation of energy, because all this is telling me is that if I add up all of my types of energy, it doesn't change unless there's an outside force, right? So, but this is for all one continuous one continuous thing. So the common usage of this is going to be something like you have water in a pipe and it's going to flow uphill, right? What's the velocity going out compared to the velocity going in, right? Well, this makes sense because it's going to be different, doesn't it, a little bit? Because, well, it takes energy to go up. It takes some of that energy. So we're just trading kinetic energy for potential energy. So we're going to be using an equation that looks like this. But because usually we're dealing with water and things and fluids, we're not dealing with a fixed amount of mass. It's hard to do that because, like, it's a fluid. Like, I mean, this a single drop. Do I mean the mass in the whole tube? It gets weird. So it's much better to work in terms of densities. So we actually is much more useful to work with the Bernoulli's equation as originally written. All right. So I think I'm going to call this one quits, just so you can try and watch these videos in bite-sized chunks and try and keep them as relevant as possible to what you want to learn. So I'm going to do an example problem in another video. So have a good day, guys. Stay safe out there.